All right, hi everybody. Sorry for the short delay there. We have been talking about cyclic loading and fatigue. And we talked a lot in the last class about the order of things, right? So if you have a fatigue problem, what's the order of solving it? And we said first you choose a material, then you find your SNP curves for that material as detailed as they exist. You account for a non-zero mean stress. And then after you solve it that way, you might modify your allowable stress using the Marin factors, and then you would solve for some dimension. So we're going to continue thinking about this today. And instead of going through that process and accounting for non-zero mean stresses, we're going to modify that. So I think it was like step 3, account for non-zero mean stresses. All right, we're going to expand that to multi-axial stress states. Oops. Okay, so that's what we're going to do today, and then I'm hoping to get through the example in the book as well. So we're going to use the book example at the end of chapter 7 as our motivating problem. So we've solved some problems already, and those only had a normal stress, an applied normal stress. So now we're going to have an applied torque. So we're going to have a beam that's fixed at one end attached to the wall. It's got a circular cross-section and some sort of a torsional moment applied at the free end. And we want to know for the torque applied of 1,500 inch-pounds, so we have a defined load here, what diameter should we choose such that it withstands 5 times 10 to the 8 cycles of what the book says is released torsion. Okay. So this is not actually a fully reversing torsion. It's a released torsion. So it's applied in one direction, and then it's released back to 0. And then it's applied in one direction, the same, and released back to 0. So you can see now that we have our kind of our stress state where everything is a minimum is just going to be 0, right? When we think about those fluctuating stresses. The other ones, however, are going to be either positive or negative with a mean stress that goes one of those directions as well. The problem statement tells us this is aluminum, alloy that is given in one of the graphs in the book, 2024-T4, and it has an ultimate strength of 68 kPSI and a yield point of 48 kPSI. So if we go and look back at the figure that they give us, they really, for the problem statement, the only reason they're giving us the material is so we can look up and see that there is at, I think it's 10, yeah, so they say at 5 times 10 to the 8 cycles, it has a fatigue strength, so sigma n is our fatigue strength, of 20 kPSI. So we'll use that later on in the problem because we recall from the modified Goodman criterion that for non-zero mean stresses that this fatigue strength is one of the properties that we need. Also, the the ultimate strength, and the yield point, right? And it's sort of the combination of those things together with our stress state that we need to solve the problem. Okay, so that's our motivating problem. And so what is the actual issue? Well, we have had normal stresses in the past. And if we were to look at this problem in a static sense, we would say, oh, I'll apply the distortion energy theory, I'll calculate the von Mises stress, compare it to the yield stress, and that will tell me whether I've yielded or not. And the von Mises stress is a combination of all those principal stresses. But so far, even with the modified Goodman criteria, we've only talked about uniaxial stress. So we only have sort of like, sigma 1 goes from some value down to 0. And so now we have a bar and torsion, and so we need a combined metric in order to handle that. There's no single common approach for multi-axial fatigue, but we have to make a couple of assumptions, and then we can start to solve it. So the fundamental assumption that we'll use is that all of the directions of loading and the stresses are going to be cyclic in the same phase, let's call it. So they all align, so that when we have a maximum stress state, it happens all at the same time. And then it might be released, or there might be a less extreme stress state, and then it goes back up. So they all happen at the same time. The other thing we have to say is a fundamental assertion, which we also used for static failure theories, which is we're going to define a metric or a modulus for the multi-axial state of stress, right? So we could think of back of like von Mises stress, right? It's combined state. And then if and when the range of that modulus for a cyclic loading in a multi-axial stress state surpasses that for a uniaxial stress state, then we can say we would expect it to have a fatigue failure. Okay? So it's the same sort of mindset that we're going to use to come up with some failure criterion for multi-axial fatigue. So let's go to the next slide, and let's recall what we had for the distortion energy theory. So the textbook is very comprehensive here. It starts with normal stress theory, Tresca, distortion energy, and then it even, I think, has one additional one, and it goes through how you might apply multi-axial analysis to all of those. And so I would encourage you to read that as you're interested, but the one that I'm going to show today and the one we're going to focus on is the von Mises stress and the distortion energy theory, okay? Because it's the one that's most appropriate for ductile materials. So if you recall, the distortion energy theory says that failure is predicted if some factor with a combination of stresses, right? So I'm going to write it out here just so that we can see the similarities of things. So it's just the difference of all the different combinations of principal stresses. So if that factor, and then we take the square root of that whole thing, is greater than or equal to some failure stress, then we would expect that thing to fail. And so if our failure stress we're defining as yield, we put yield stress in there. And this equation was in part related to the distortion energy for any state of stress. So the distortion energy is UD, and it has sort of a similar form. It's kind of a half And then it has a coefficient out front, which helps us go sort of between stress and energy. And then it's got all those same combination of factors. Okay, so this is kind of one part of the background of what we need for today. We are going to use this distortion energy as our metric. So we're going to derive an expression for this in a uniaxial stress state, and then we're going to put that back into our multiaxial stress state to define a failure criterion. And the failure criterion that we're going to start from is the modified Goodman criterion. So I'll write just so the modified Goodman criterion was that kind of crazy plot which had all those regions depending upon where the mean stress fell. Right, so we had like region, we had A, B, C, D. Right. And so if we focus on one region, which is just region A, and it really could be any of them. But for this, let's focus on this one first because it just gives us a failure equation to work from. And so in region A, we had this failure criterion, which is the maximum normal stress minus 2 times the mean stress greater than or equal to the yield stress. So if we had that, then we would predict a fatigue failure. And so it was kind of in the far sort of bottom left. Okay? So this is our failure theory, and then we had the metric we're going to use, which is the distortion energy. So if we work from the distortion energy, UD, and we have in our example problem, we have a bar that's twisting, and then the load is released, and then it's twisted again, and the load is released, right? So we don't just have one distortion energy. We have no distortion energy, and then when the load is fully applied, we have our maximum distortion energy, right? And then we have everything in between at some point as well. So we need to describe the maximum, the mean, and the minimum of this metric that we're using, this distortion energy. So we're going to say that we have distortion energy maximum is equal to, and we had an expression, and instead of the principal stresses, we're going to put in whatever the maximum of that principal stress is. And not the maximum magnitude necessarily, but the maximum in time. Okay, so I'll write that out here. So we'll have the same coefficients out front as we had before. And then in the expression, instead of sigma 1, we're going to have sigma 1 max minus sigma 2 max. All right, and we'll add on our other ones, sigma 2 max minus sigma 3 max. And so keep in mind, I'll write it up to the side, maximum does not indicate necessarily a magnitude here, but it indicates the max time, right? The maximum stress state in time that we've defined as our maximum. So this is, we can write this definition for UD max. And we could write the same for the mean and the minimum. Right? And I just described when those would happen in time for our sort of characteristic example of that bar and torsion. I'm not going to write out those same equations for the mean and the max. All it is changing subscripts. But we have all three of these equations. Okay, so we have that now. So let's go through and derive whatever UD max would be for a uniaxial stress state that we are very familiar with. Right, so I'm going to write sort of up at the top here. And so for a uniaxial stress state, sigma 1 is the same thing as sigma max. And that's just what F over A, right, or whatever the expression is for normal stress there. The other principal stresses are 0. Right. So now we can go through and cross off anything with a 2 or a 3. So now we're assuming that our axial stress is the cyclic stress, right? And we're going to equate it to that. We're going to equate our multi-axial stress state to that. So I'm going to cross off kind of this sigma 2 and 3, sigma 3. So you can see that we have kind of a sigma 1 max squared. We got 2 of those. And then we have a factor of a half out front, right? So we end up with just this coefficient term, that's material properties, times sigma 1 max squared. And I'll write that on the next slide.
Is everything in this bracket supposed to be square rooted?
No. So the when this is translated over to a stress, yes.
Okay.
But when it's an energy, no. Okay. So we can write UD max is our coefficient, 1 plus nu divided by 3 modulus E times sigma max squared. Okay, helpful. And if you recall in our Goodman, or modified Goodman, we had sigma max, we had sigma mean, and sigma min, and then we also had some of our other yield point and ultimate stress. So we had these three. So we don't have distortion energy in there. So we have to translate back from this into a stress. So we're going to solve for sigma max. So we're just going to, put everything on the other side and take the square root. So we will come up with the square root of the inverse of that coefficient times the square root of, and I'm just going to keep it separate for terminology's sake, times the square root of the maximum distortion energy. Okay, so far so good. Now let's think about the mean. Oops. Pen, okay. So let's also define UD mean, or just little m. And so for our uniaxial stress state, if we go back and think about that, our mean stress is just half of our maximum stress. Right? If we're going from 0, so if it's not fully reversed, we're going to go from 0 up to sigma max and back. So our mean stress is positive and it's half that value. So we can write a similar expression for this one, where instead of having the subscript as 1 max, 2 max, 3 max for all the sigmas, we're just going to have the mean stress there. And we will come up with something very similar. Instead of the maximum stress, we'll have a mean stress. So I'm just going to write that here. If we go through the exact same procedure and cross out the exact same terms. Then we'll solve for the mean stress. As a function of the mean distortion energy. Okay. So for sort of region A of that modified Goodman diagram, we don't actually need the minimum. So region A, I'm just going to recall that here. It was sigma max minus 2 sigma m, or mean, greater than equal to the yield point, and that was our failure criterion. So I'm not going to calculate the minimum, but you can see how the same thing would apply. So if this is our failure criterion, now we have expressions for sigma max. All right, so I'll outline that one up here in red. So we're going to plug that one in. Now we're going to plug this one in. And that will be helpful. And then we'll go back and we'll define this for our example problem. Now that we have a specific failure criterion to apply that includes fatigue aspect and multi-axial stress. So I'm going to plug those in on the next slide here. So we will have our sort of coefficient out front, 3e divided by 1 minus nu to the 1/2, or that's the square root. We had that in both of them. And then we'll have our ud max, the square root of that, minus 2 times the square root of ud mean. And if that is greater than equal to the yield point, we would expect a fatigue event question. 1 second.
The failure criteria on the previous slide, is that saying that as long as the stress is less, or sorry, as long as the stress is greater than the yield point, then the material won't fail?
No, this is saying that it will fail.
Well, it is greater than that.
Say one more time.
So if the stress is greater than the yield point, then it will fail.
If the combination of stresses is greater than the yield point, it will fail. Correct. Yep. Good question. Ryan asked, where did the 1 minus v come from? It's not, it should be 1 plus v. Didn't come from anywhere. Okay. So this is our combined failure equation for region A. And the same thing can be done for the other regions, right? It's just different combinations of mean stress, max stress, and minimum stress, and then the constant R. That was just like a ratio between the fatigue stress and the ultimate stress. So now let's go back and solve our problem. Okay. So to solve our example problem, we need to know, we need to define our principal stresses, because everything here is based off of principal stresses. So let's get an expression for those, and some of those will be 0. So that's going to be helpful as we move through the equations. So if we have a bar in pure torsion, right, we could go back to our stress cube, define the stresses, solve the cubic equation, come up with the principal stresses. But I'm going to, instead of go back through that again, I'm just going to draw the Mohr's circle, because we should all be familiar with that as well. So the Mohr's circle for a pure torsional shear stress is just a circle whose origin is at the intersection of those axes that we always plotted on. So normal stress on the x-axis, shear stress on the y-axis. So this is a state of pure shear. And so we can say for pure shear, right, if we think about our principal stresses, sigma 1 will be here, sigma 3 will be here, sigma 2 equals 0. And then also sigma 1 is the same as the maximum shear stress because it's a circle, right? That's why we use Moore's circle. And the sigma 1 is going to be the positive value of tau max. Sigma 3 is going to be the negative value of tau max. So I'm going to say negative and then absolute value. So we always know it's negative. We always have that correct order of sigma 1 greater than sigma 2 greater than sigma 3. So now I want you to sort of do a thought experiment on the Moore's circle. Instead of having a static Moore's circle, as we apply shear stress to the bar, you can envision that we apply the load and the Moore's circle grows, and then the load is fully removed, and then the Moore's circle collapses back to like a singularity, right? And then the load is applied again, Moore's circle expands, and then it goes back down. So this is going to help us define our maximum, minimum, and mean for each of these principal stresses. That's how we're going to think about it. So the first one, sigma 1, is going to be equal to the absolute value of the shear stress, right? And we'll put in an expression for that later, but it's kind of like, or it is exactly 16 times the torque moment divided by pi d cubed, right? If we want to put in our dimensions. I'm not going to substitute all of that in right now, but that's kind of what we're looking forward to. So that's sigma 1, and so sigma 1 is fluctuating, right? Because mt is also fluctuating, that torque load, when it comes up and down. So sigma 1 max, right, is going to be equal to just tau max. Sigma 1 mean, or 1m, we'll call it, is going to be 1/2 of that. And sigma 1 min is 0 because it's a fully, they call it a releasing stress, okay? So these are the three values that, that we needed to plug in and get our strain energies, maximum, mean, and minimum. So that's just for sigma 1. So we can do the same thing for sigma 3. So sigma 3 max is going to be equal to minus, bless you, absolute value of tau max. Sigma 3 mean is going to be 1/2 that. Whoops, tau max. And sigma 3 min is also 0. And all of the sigma 2s are 0, so we don't have anything there. So you might be looking at this and saying like, okay, wait a minute. How can a maximum value be the negative of our applied shear stress? Right, normally when we say something is the maximum, it's not a negative, especially if we've defined everything very specifically. And so this goes back to that definition that I had before. And so max here is just the designator that means it's our extreme stress state in time, or it's our maximum stress state in time. And so when the stress is the most extreme in time with our fluctuating stresses, we're calling that max. And at that time, sigma 3 is going to be, the maximum of that will be, or that value would be minus tau max. All right. So now we have those. So let's calculate our maximum distortion energy. UD max. All right, so we have our coefficient out front. And then we have all of our combination of terms, right? So sigma 1 max minus sigma 2 max, 2 max, square that. Then add on the other combination, sigma 2 max minus sigma 3 max. And sigma 3 max minus sigma 1 max. And now we'll start canceling out some terms because all of the sigma 2's are 0. So we don't need any of them. So we'll do this one, this one. So you can see that there are still all 3 terms left. So in the first term, we have sigma 1 max, which was absolute value shear stress. Then here we have minus sigma 3 max, which turns out to be plus tau max. And then we had their difference, right, which is 2 times tau max. And I forgot a factor of 2 out front, or a factor of a half. Come back. Sorry about that. Okay, so if we have a half out front, then this ends up being this expression here, UD max is equal to our coefficient times 3 absolute value tau max squared. Okay. And so this is just algebraic manipulation. I would encourage you, if you want to see all the algebraic manipulation, go back after class and just spend some time working through that. I really want to get to kind of like the answer today. So that's why I'm going to keep pushing forward. We can do the same thing for the mean. And we can write out the whole equation of the combination of stresses, except for instead of sigma 1 max, sigma 2 max, it's going to be sigma 1 mean, sigma 2 mean, and then all the combinations through there. And then if we plug in those values that we calculated from our problem, we come out with something similar, which is 1 plus nu over 3 times the modulus. And all it has is a different little coefficient inside here. It's like 3/4 times tau max squared instead of 3 like we had in the top one. Okay. So this is what we needed to check for in our failure criterion for region A, right? And so we can go back now and think about what region are we even in, right? Like, can we use this equation? Is this equation helpful? Not helpful? Do we need to go back and look at the other ones, right? And so if you recall, regions A and B were at the left side of the plot. So that has a mean stress, let's say less than 0. And then regions C and D, because it went from left to right along the x-axis, were for a mean stress greater than 0. So let's make a plot of our stresses that we have, right? So we can keep this straight. So let's first do sigma 1, and we'll just draw it in time, right? And so this is a fully releasing stress, and so you can think about that Mohr circle expanding and contracting. So at time 0, we can say it's at 0, right? And then it goes up to a maximum and back to 0. And the magnitude of the maximum magnitude there was the absolute value of tau max, right? So that's the maximum, and then we also had the mean, which was 1/2 of that. So that's what's happening in time. So if we look at just this component of stress, this component of stress has a mean stress greater than 0. Okay, so that means we should be in region C and D, Now let's look at sigma 3. Uh-oh. So now we're actually going to have the opposite, right? So our sigma 3 at that same time, if these are both in phase, right, starts at 0 and then goes down to minus absolute value tau max, right? So then the mean sigma 3 is half of that. And so now our mean stress is below 0. So now we're in region A or B, right? So in this case, we have to check all of them because we can't say for certain which one is going to cause the failure first. And so we're going to have to check all of them, because different components of the principal stress have different different mean stresses above and below 0. Okay, so let's look at these regions here, and we will solve for what a diameter would be in each region, and then we'll compare them. Okay, so region A, that's the one we derived in the first place. And so we had an expression that was, it will fail if, right, there was a coefficient out front, 3e, and you don't have to write it again, I'm just going to write it up here for reference, to the 1/2 power, and then we had ud max, right, we had the square root of that, minus 2 square root ud mean, greater than or equal to the yield point. And so we plug in now our expressions for ud max and ud mean, okay? And then we come out with a long expression. Okay? And I'm not going to write that expression here, but if we simplify that, so substitute in ud max and ud mean, we actually find that it gives us a non-solution. We find that it gives a solution, it like cancels everything out. And so it comes out to the yield point has to be greater than or equal to 0. And so it doesn't really make sense. So we're not going to consider region A for this case. All right, so moving on to region B. So for region B, this was at the end of the last lecture, we kind of covered this, was sigma max minus sigma mean is greater than or equal to the fatigue strength, sigma n. So we can go through, I didn't do this here in this lecture, but we could go through and determine what this expression would be if we use that metric of the distortion energy. And so we can come up with a more specific equation for failure, which looks like the other one, but it's not exactly the same. So it has, instead of a 2 in there, it just has square root ud max minus square root ud mean is greater than or equal to the fatigue strength. And if we plug in the expressions we had here and here, we come up with a very simple expression. And also those coefficients cancel out. So we come up with square root 3 over 2 times tau max is greater than or equal to the fatigue strength, sigma n. So this is for region B. We've gone through a lot of analysis to get to this. And so now we're going to plug in for tau max, right? So tau max was equal to 16 times the torsional moment divided by pi d cubed. So square root of 3 over 2 times that. And so we have this expression, and now we're going to solve for d, because that's what we really want, right? So if we solve for d, we come up with, right, d is equal to the cube root, because we had d cubed on the bottom, cube root, and then we have some constants in here, 8 times square root 3 times the maximum moment, divide by pi times fatigue strength, sigma n. Okay. We can recall that our maximum torque moment was 1,500 inch-pounds, and the fatigue strength that we read off was 20 kpsi. So if we plug those in, we will get some answer. And then what the book does here is they want us to have a safety factor of 2. And so we're going to put a safety factor of 2 onto that fatigue strength. So instead of fatigue strength, we're going to do fatigue strength divided by 2. So if we put in that here, so I'll just do sigma n divided by 2 on the denominator, we come up with 0.87 inches. So we got an answer. All right. All right, so questions as to how we got to this part. Question here.
Why did we stop at region B if from the charts we drew nobody said we had to check all the regions?
Because I just didn't say it yet. So why did we stop at region B? Because I didn't say C and D yet. Question here.
For the region A,
Yeah.
you said that the sigma yp being less than or equal to 0 is nonsensical. Is that because given the yp is 48?
Yes. Yep. And the yield point, the yield stress is always positive, so it can't be less than 0. Yep. Okay. That's true, yes. So we are at the end of our lecture time for today. There are 2 more domains to check. And so you will find that if we check them, the answer is we need to use region C, because that gives us the largest diameter. Okay, so it gives us a diameter that's larger than 0.87. And we have to choose the one that is going to withstand the stresses in that region and also whatever would happen in the other regions. So if we choose the largest size of shaft, then it's it's expected to last all those 5 times 10 to the 8 cycles. Okay, so we'll end there for today. I'll see everyone Thursday. Question?
What is that number if we solve ourselves?
0.95. It's also in the textbook if you want to read that. Yeah. Yep. All right, so I'll see everyone on Thursday.